All right, thank you very much. I'd also mention that be liberal with the input that you accept, but check it. So even though that open API is very open, you still should check your input. Anyway, I'm Clint. We're going to talk about zero trust overlay networks. As everybody has, they have a slide about me, and as you can see, that's definitely not me, right? Like, this is my buddy Philip. Philip works at NetFoundry too. Philip said to me one day, developers don't care about security. And I said, Philip, that is not true. We all care about security, right? Right. So the problem, of course, is that developers are busy. We're busy trying to develop actual software. We're not busy, talking to business development people like Philip does. So I went to Google, and I said, hey, Google, do developers care about security? And it's pervasive, right? Like, this is a thing that the world thinks developers just don't care about security. So my plea to anybody who's not a developer in this room, give your developers time to secure their software. Joel Spolsky invented Stack Overflow along with other guy, I can't remember his name. And he has this quote that has stuck with me for 15 years. Shipping is a feature. Your product must have this feature. Well, in 2024, security is also a feature. Your product should also have this feature. So please make sure you give time to your developers to secure their APIs, because as we all know, APIs are terrible and untrustworthy and a security risk. All right, so everybody thought, oh, we got a zero trust overlay mesh guy. Like, this is gonna be the best thing ever, right? So my goal in this conversation is to get you from this to this, right? So we're gonna put zero trust in your APIs and you're gonna like it. All right, so here I'm Clint, a longtime developer, I'm a nerd. Been working with Java, C#, C, Golang is my latest hotness. Love Golang. All right, so what is a secure by design API? We want that thing, when it comes out of your head, out of your keyboard, to be rock solid and steady, right? So it should be developed with the strictest of security, the least permissive of permissions. And today, since I'm talking about overlay mesh networks, that's going to be talking about network security and network connectability. Everybody here knows who the beast is, but not everybody knows who the beast is, right? So the beast, if you don't know, the beast is this really cool limousine that the United States president drives around in. The beast has all of its security built into it, right? It's not available to be seen from the outside. You don't know where to attack. You don't know what's going on in there. You just know it's sleek and it's secure. Take the Mad Max approach. Mad Max has just a bunch of armor plating all over the place. You know exactly where the chinks are in the armor. You know exactly where to attack. So we want our APIs to be like the beast and not like Mad Max. Zero Trust has a whole bunch of pillars, but I like these three the most. I think they're the most germane to software engineers. Strong identity, least privilege, and continuous authorization. What is a strong identity? When I think of a strong identity, I think of something that is cryptographically verifiable. That is the key to a strong identity. What does that mean? That means an X509 certificate, that's what we use every day. You may or may not know it, but X509 certificate is signed by an authority, right? So there is some authority somewhere that said this here digital document was signed by, Google or VeriSign or whoever. And so you can build a chain of trust from one certificate all the way up until a certificate chain that you actually can trust. Oftentimes, it ships with the operating system. So on your phone, on your computer, there is a CA bundle. Not always. Your software can be configured to ignore that bundle. And so you can pull your own bundle. If you want to keep your trust zone from this to this, you can go ahead and have your own CA bundle and use that. A JWT, all right, JWT, JOT. What do you think? JWT, JOT. Anybody heard JOT? No, because it's a terrible term. JWT is what I say, but a lot of people call those things JOTs, JSON Web Tokens. A JSON Web Token is also a signed document. It comes in 3 pieces if it's signed. It's base 64 encoded with 2 little periods in there. If you don't see 2 periods, you do not have a strong identity because it doesn't have a signature. There's a header, there's the body, and then there's a signature. That signature is really important. That's what actually tells you the authenticity of that document. The signature also needs to be verified somehow. So the thing doing the verification needs to have a key, a public key, that's been shared with it, or you need to be able to access a JWKS endpoint. So when you see OIDC, OpenID Connect works like this. So OpenID Connect will use a bunch of JWTs, you'll get them from some authority, and you'll be able to pass those around as bearer tokens, which you've maybe seen before. Maybe you've used them. Continual authorization basically is what it sounds like. You're going to inspect the state of the system continually. And if it is failing some sort of posture check, you're going to eliminate connectivity from that device or that application to the rest of the overlay network. So you need to be able to continually authorize a connection and make sure it's not only valid once, but continually valid. Least privilege. Here it is, right? This is Dolly, right? Can't do letters. Crime scene, right? So least privilege is all about controlling access. So you need to authorize every single piece of connectivity on an overlay network. Now at first, when you go home and you go, that Clint guy, I need to get this overlay network thing. Let me go look at it. You're going to look at it and you're going to go, oh, whoa, this is complicated. Because you can't just turn it on and connect things, right? Least privilege, right? So you can't just turn it on and connect the thing. You've got to go through and you've got to authorize the server. Hey, this server is allowed to bind. Then you got to go over there and you got to authorize clients. These clients are allowed to connect. And so that's a little bit daunting at first. But once you get used to it, it's actually quite simple. So I think give it a shot. But it is a mind flip. Most people are not used to dealing with identity. IP addresses are not, everybody, IP addresses are not identities. All right. So what's an overlay network? That's kind of what it sounds like. I always consider mine built on the internet. We had, I think he left, but he had a great thing about the other day about everybody having, every device being its own bastion, if you would. So the internet is your overlay network. On that network, you'll place these things called routers. Routers are what they sound like. They route traffic. But they're not hardware routers, they're software routers. Those software routers will connect to one or more controllers. Those controllers are the policy decision makers. They allow you to be authorized to the overlay network, and they decide whether or not you're allowed to dial or bind services. They connect to each other to form a mesh. That mesh, little lock icons mean mutual TLS. So everything in between these two, mutually TLS secured. And that's all to service the edge endpoints. So we have edge routers, the things that your devices connect into. Then you have the core routers, or the fabric routers, if you would, the things that form the mesh. By the way, edge routers can be part of the mesh, so there could be a line going between the bottom one. And then you have your network, or your overlay network aware clients, which are allowed to do one thing, and that's just send traffic, right? And so that's the whole job of an overlay network. But it's supposed to do this really fast, right? So you need to do this as quickly as possible. If one of those things go down, you want it to heal itself, and you want it to look something along like this, right? So you have 6 routers here. You have them all interconnected. They're all meshed together. You have self-healing network. If one of your routers goes down, you want it to be able to send traffic from one spot to the other spot. You want optimal routing. So sometimes to get from, where's the green button? I was told there was a green button right here, yeah. So to get from the router in the upper left down over to the router in the lower right, sometimes it might make more sense to actually go all the way across the top and down because of something called the internet weather, right? We have a developer who was doing a lot of performance testing one time, and he was testing from, I think it was Singapore to Sydney, and was shocked that sometimes the traffic would go through India. Because, I mean, that doesn't make any sense, right? Just geographically, it's a big triangle. But because the internet between Sydney and Singapore was so busy, it was actually faster to route in other directions. So the overlay network should maintain some sort of path routing for you, and also active load balancing. So if you have an overlay network that you need to be authorized in order to access, you'll first ask, well, maybe not first, but you'll eventually get to the point where you're like, man, what about my load balancer? My load balancer's out there just load balancing TCP, raw dogging the internet. What am I going to do with that load balancer? Or what am I going to do with my web application firewall? Do I not need those in a zero trust overlay network? If you have identities that are on that overlay network, I'm going to say no, you don't need them. But that doesn't mean you'll get rid of them at all. Because for the longest time, you will still have underlay, I didn't really talk about underlay traffic, but IP address traffic, right? You will still have IP address traffic. You'll never get rid of those firewalls. You'll never get rid of those load balancers. Okay, authorize before connect. This is another interesting feature that I think that a good zero trust overlay network should have. Authorize before connect means even a single underlay port that's available is too many, right? Land and expand is not just a euphemism, it happens all the time. And so if you have one port that leads you into your network, then you can have, into your safe network. We've all seen the castle and the motif, right? I've used it in presentations before, but if you get into the castle, you're free to roam about the castle, enter all the doors. So instead, we want every single device to have a firewall like this, so that even one port is too many ports open. So this is what that would look like. You'd have a user on the left, they attach to their overlay network. You have a server on the right. It also attaches to the overlay network, but it establishes an outbound connection out through the firewall, so no inbound firewall holes. That way, even if your server does have ports on it, well, I guess I can point. Even if your server does have ports on it that are listening on the underlay, you can keep it behind the firewall. It doesn't have any ports open to it. Still recommend not doing it that way, but we'll get into that in just a second. There are still ports open, so a common knock of a design like this is that, you're just moving the port from over here to over here. And that's true. That's exactly right. All you have to do is attack that port now. But you have more than one port that you can be attacking. Now you have to attack all those routers all at the same time. They can be geographically distributed. It all just mesh, because it's a mesh network, it all just knits itself together. So it is true that you do move the firewall or move the port from one place to the other. But this port is generally vastly more protected than the other one, just based on the fact that it requires a strong identity, it requires an authorization, it requires a lot of things before you can even compromise that particular port. These are the 3 tiers of zero trust as I've defined them. Some people have, I've never seen anybody else define it like this, but this is how I talk about them. ZTNA you've seen before. ZTNA is what most people consider to be zero trust. Look at that. Look at the trusted zone, it's gigantic, right? So you have your local network that you have to trust when you have a network router to network router zero trust zone. That's no different than going over the internet. Better is when you have a zero trust host access type of situation. Here we have more firewalls in the way, and this is exactly what we were talking about yesterday, when every single device has its own firewall around it, its own little zone. True micro-segmentation. I didn't use the term, but maybe people know that word. So here, every device has the firewall. Every device is its own little world, and you can only access that device if you are on the device. And so any application that's on the device that is available to talk to the server, so on the left side here, if any device, any application on the device can talk to the server over here. So even a rogue application, so if you were, say, having an application that was in the browser and you had that browser open some JSON, or a web request from the browser to the server, when you have zero trust host access, anything on that local machine has access to whatever that device can connect to. Generally speaking, that's not a particularly large amount of attack vector. So you've taken the attack vector of basically everybody down to the attack vector of just the devices and identities that you have chosen to trust yourself. The next level of zero trust is something that not many places do yet, which is application embedded zero trust. And that's really what I want to talk to a bunch of developers about. Because with application embedded zero trust, you take the notion of that zero trust agent and you move it all the way into the application. That has a big benefit because when you move it all the way into the application, now even malicious apps that are on that particular server itself or the device itself, those side channel attacks that you've heard about so many times, they can't be performed anymore because this application only can talk to the server if it has a strong identity. And that application has to be compromised before you're able to send any data to that server. So now you've reduced the blast zone tremendously, but you can go one step further. All right, so before, you still trust the host operating system. So oftentimes, that will mean a key saved someplace securely, someplace that root only has access to, or using a key chain or something along those lines. But if you use a hardware root of trust, so if your Zero Trust Overlay Network supports a hardware root of trust, something that you can remove from your laptop, then you don't have to trust the host operating system at all either, which is really cool. Because if you have a YubiKey or something along those lines, there are many hardware tokens, is what they're called. There are many such things. You can actually remove it from the device. And when you remove it from the device, it's no longer capable of performing the cryptographic operations to get you onto that overlay network. End-to-end encryption is a vital task of any overlay Zero Trust network. So you must have end-to-end encryption. If we take a look at this, this is a simplified view. We'll see a little bit more complicated example in a second. We have the green pipe, which is mutual TLS. And what that will be is that is the connection between routers, right? So when you have a point-to-a-point mesh network, you always have a bunch of connections. Those connections are all mutually secured. If somebody were to be able to get onto that router, compromise those keys, it's possible that they're able to now snoop all your data. So one of the first questions we get is, what does it look like when somebody compromises one of these routers? Well, end-to-end encryption is your classic answer to that. In an end-to-end encryption scenario, only the initiator, only the termination endpoint are able to decrypt the traffic between each other. And then you have your application connection that rides through those two pipes. So if your application connection also has some sort of encryption available to it, should somebody be able to defeat the end-to-end encryption or find whatever that key is and snoop the traffic and decrypt that traffic, then you can still have application encryption if you were using, say, HTTPS instead of HTTP. So here's what that looks like in one big slide. Here we have a bunch of routers, and the routers connect to one another. And between those two routers, you have a green mutual TLS connection, and then you have an orange mutual TLS connection, and you have a red mutual TLS connection. This blue pipe goes all the way through. This is your end-to-end encryption. Then you have your application protocol, whatever that is that you're running through that whole big pipe as your secure application protocol. Why is TLS not enough? Well, if you look at the top, it looks pretty complicated and it's a lot of colors. I don't know if it's too many colors, but on the bottom, we have opportunity for a malicious person to be inserted into the middle. And so this is actually what happens all the time in corporate America, right? If anybody's ever seen the Cisco Umbrella client running on their local computer, that thing's doing DPI, or deep packet inspection, and it's checking out what you are doing and where you're going and why. So even though you have TLS and you see a connection, it's entirely plausible if you have an enterprise laptop delivered from your employer that that laptop is able to see everything you do and everywhere you go. We're going to look at a little bit of code. I don't know how much time I got, but here's an example. I'm also going to talk about something, if you've never heard about it, called Spiffing Spire. So think about that for a second. Here we have a really simple setup, right? On the right-hand side, we have a client that wants to connect to some particular server. Here's what that might look like in Go. Hopefully, it's pretty easy, right? Go is actually a pretty approachable language. You can see we're just making a new server, and we add a couple of handlers to that server, and then we return the server. And so that's how we create our server. Very basic Go. Then what we'll do is we'll say we listen on the TCP underlay network, again, TCP IP underlay network, and we're going to listen on whatever the port is. And I had a slide that told me what port, but it doesn't matter. So let's say it's port 8000, or did I actually say what port it was? No, I didn't. Yeah, I did. 18080. All right. And so now we have a listener that is created that now we serve from our HTTP server. Again, no TLS. So there's 18080. All right, cool. So that's our basic no TLS server setup. mTLS was Spire. Has anybody heard of Spire? Wow. Oh, totally worthwhile. Spire is the reference implementation, hence the RE, of the spiffy set of contracts. I can't even come up with the right term at the moment. RFCs. I don't know what to call it right now. So it is a set of specifications. There it is. It is a set of specifications that define identity. And so spiffy is very approachable. If you've never read it, go out and check them out, read them. It's like six of them, and they're all tiny. You can read it. But Spire is an implementation of spiffy. And what Spire can do is with a Spire server and with Spire agents, it can do something called workload attestation. So workload attestation is a cool, fancy term for just some little agent that sits on your computer that can read the operating system and then make assertions about that operating system, whether you are on Linux or not. So this is that policy enforcement or that continual authorization type of thing. Whether you are running the latest patches, whether a process is running, that sort of thing. And then it can attest that you are who you say you are, deliver certificates to you, and let you implement mutual TLS. So now we have mutual TLS in like 10 lines of code. You have to deploy agents, so like, there's a little bit of a pain there. But once you have that set up, it's actually really good. So here we're still creating that common server. Oh, actually, maybe I got to build. I do. Creating a common server. We're going to configure it for mutual TLS. And what that means, configure it for mutual TLS, means we're going to make a new X509 source using their workload API, which is from Spire. And then once we've done that, we're going to create an underlay listener with a secured port, which I think is 18081, and serve TLS. And that is literally the code. Like there's no little ellipses in here. There is other code. I'm just kidding. There is some boilerplate. You can always go and find that out, or if you're interested, ask me and I can show you where it is. So we're going to do the same thing with an OpenZD. I should have said OpenZD is an overlay network, totally open source overlay network. I work for NetFoundry. NetFoundry supports the OpenZD project. OpenZD is an open zero trust overlay network. So here we can integrate mutual TLS with OpenZD, doing the same sort of thing. But before, we do have those ports are open. 3022 is open on the routers, but my server has no open ports. And my OpenZD client doesn't connect directly to my OpenZD server. It goes through this router. And so to do that, we will create, I'm about that time. So we have these things we call external JWT signers. So before we were talking about JWTs being strong identities. You can use those strong identities to authorize yourself onto the OpenZD overlay network. You can then create an authorization policy. The authorization policy is used to tie that external JWT signer to authorization. You have to be able to be authorized to get onto the overlay network. You've got to create strong identities. So you create two strong identities, one for your client and one for your server. And then you have to authorize. See what I mean before? It sounds daunting, right? So then you have to create configurations. These configurations tell your computer how it's going to actually access or it'll tell your program how it's going to access the particular server at the other end. And then you have to create a service policy to authorize them. So here we have a bind policy. Here we have a dial policy. The bind policy is what lets the server decide that it can bind ports on the overlay network, not on the underlay network. And the dial policy allows me to connect from the client to the server. That looks like this. There is a little bit of like create OpenZD listener, I think is a little bit of extra. But here we'll fetch our JWT from Spire, and then we'll use that to create an OpenZD listener, and then we'll serve that listener. All right. Does anybody have any idea what this might be? It is the longest route on the earth that you can walk, and that represents your path to zero trust. We've heard a lot of people talk about this already, right? Like everybody, timelines from the fellow earlier this morning. You might start down here in South Africa and get distracted by the pyramids in Egypt, but you're not going to start off from one place to the other, and you might need to start, all the way at the beginning. Once you have an overlay network, you can start your journey wherever it fits for you. So if you are so lucky as to be working on greenfield stuff, you can start in Siberia and just go application embedded zero trust right from the beginning. Who does that, right? So instead, you have to have an overlay network that will support starting at one end or the other end, depending. Zero trust network access, oops, down here, or zero trust host access, somewhere here, zero trust application access over there. All right, so here's a good little summary slide. These are the kinds of things that I think a zero trust overlay network needs to have: strong identities, continuous auth, that least privilege, multi-factor authentication. I didn't talk about that, but that's very important. So you should have native multi-factor authentication, whether that be time-based one-time passcodes, TOTP, or it be integration with an IDP. So single sign-on is a common requirement. Don't get me started on single sign-on. I don't understand why everybody loves it so much. It seems like a terrible thing to me because that, like, phishing attacks are real, right? So if you're going to do single sign-on, please make it the second factor and not the first factor. Don't let it just open the door all the way in. And, you know, I don't understand why people love SSO so much. Have something that is a second form of authentication. Do not just rely on just SSO, but boy, is it easy. And security is always a trade-off, right? Trade-off between what's good and what's easy. Let's see what else. Authorize before connect is really important to me. No listening ports, that's pretty critical. Your mesh network has to be self-healing, fastest path delivery, TCP or UDP. You want to be able to support TCP or UDP if you can. Shocking how many regulated environments won't allow UDP exit. So if you're using, say, a WireGuard, I don't know, then WireGuard sometimes gets blocked because UDP is one of those things that a lot of regulated networks just don't allow you to do. And then if you can, have it support classic IP tooling, that's a bonus. But when you're using an overlay network, because of all this security that's involved, oftentimes classic IP toolings don't work. For example, I don't remember who said it earlier, but it was McKinley talking about taking an inventory of your services. If you have to authorize all of your services, you have an inventory out of the gate because you've had to go through and authorize every single one of them. But what you can't do is use Nmap to find those services. Lots of attackers use Nmap all the time, right? You're running over port 22, there goes some SSH. With a good overlay network, in my opinion, it'll all be synthesized through a single port. It'll all look like port 443, and then who knows what's going over it. It could be SQL, could be TCP, it could be FTP, could be whatever. All right, these are two projects, HTTPS Everywhere and Let's Encrypt. Hopefully everybody remembers Let's Encrypt, but HTTPS Everywhere, people might not remember because it's from the before times, right? I'm so old that I remember when we had HTTP traversing our networks and we had FTP traversing our networks, and everybody said, boy, that was dumb. We should be securing these. We should use TLS everywhere. So SSL everywhere became the mantra, right? And HTTPS Everywhere was one of these plugins that was in your browser, and it would automatically upgrade you from HTTP to HTTPS. It was as simple as that. Let's Encrypt obviously lets everybody use TLS because it never used to be free. People used to have to pay for it. And even if you pay $200, like as a lone developer, that's $200 I can just put right back in my pocket. But now Let's Encrypt does that. I would like to see Zero Trust be the next evolution of this. I honestly do believe we're going to stop allowing anonymous contacts from people, and we're going to transition from HTTP to HTTPS to Zero Trust, because I really do think it is the next evolution. It's not here. It's actually just getting a lot of steam. Nowadays, everybody knows what Zero Trust even is, which is cool. But when I started in 2019, it was barely known. This is our contact information. You can find me in all these things. So if you are interested in OpenZD and Zero Trust Overlay Mesh Networks, hit me up on any of these. Get me on LinkedIn if you want to get me on LinkedIn. And then I put these into the slide deck just so that when you guys get the slides, you'll get the longer presentation. If you're interested, this appetizer demo, if anybody, so since it's like the break, if anybody wants to do a fun demo, we can do the appetizer demo. If you have Go on your computer, we can experience application embedded Zero Trust, and I'll just hang out and we can do that. Otherwise, do it on your own. And that's what I got.